Welcome back to Math 104. We continue to assume that at the shooting range, you hit the target with probability 0.7 on each shot. You take a total of 3 shots. Now find the probability of at least 2 hits by drawing the tree diagram and reasoning out the probability as we have been doing. First, notice that the probability of at least 2 hits is the same thing as the probability of 2 or 3 hits. There are only 3 shots, so at least 2 hits means 2 or more, and therefore 2 or 3 hits. Since the experiment itself hasn't changed, neither has the tree diagram. The only question is, which outcomes count towards this event? Now, all the outcomes we highlighted for the previous problem, about exactly 2 hits, are also in this event 2 or 3 hits. Now we have the outcome heads, 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 also in the event that we're looking at. So the probability of heads, heads, heads contributes towards the probability of at least 2 hits. And the probability of heads, heads, heads equals 0.7 times 0.7 times 0.7. So 0.7 times 0.7 times another 0.7. The other outcomes in this event we have already written down. Thus, the probability that we're looking for equals 3 copies of 0.7 squared times 0.3, plus 1 copy, I'll write a 1, but you don't have to, 1 copy of 0.7 cubed, and just for the sake of emphasis, again, not because you have to, I'm going to write times 0.3 to the 0. 0.3 to the 0 just equals 1. I'm writing it this way because we're going to work our way towards a formula in which we're always going to write down probability of a hit raised to a certain power times probability of a miss raised to a certain power. In the same spirit, we can even write a 1 here as the exponent for 0.3 when there's 1 miss. So 3 copies of 2 hits, 1 miss, plus 1 copy of 3 hits, 0 misses. It turns out that this equals 0.784. So there is a 78.4% chance of getting at least 2 hits. To appreciate what's going on, let's contrast this with how the numbers would turn out if the outcomes were equally likely. What if you were not a 70% shooter, but instead a 50% shooter? What if hit and miss were equally likely on each shot? Then in the tree diagram, you would label each edge by 0.5 for hit and 0.5 for miss throughout the tree. But the outcomes counting towards the events, at least 2 hits on 3 shots, would be the same outcomes. 3 hits, 2 hits and a miss, hit, miss, hit, and miss, hit, hit. But what would be the probabilities of those outcomes if hit and miss were really equally likely? The probability of hit, hit, hit would be 0.5 times 0.5 times 0.5. How about the probability of hit, hit, miss? Oh, that would also be 0.5 times 0.5 times 0.5 by this thinking. How about hit, miss, hit? That's also 0.5 times 0.5 times 0.5 if hit and miss are equally likely. How about miss, hit, hit? Same thing. Ah, that figures. When hit and miss are equally likely, then by the time we've formed outcomes from the 3-stage experiment, those outcomes are all equally likely. Overall, then, the probability of at least 2 hits in 3 shots is equal to 4 copies of a half times a half times a half. But notice, if we write these as fractions rather than as decimals, 4 times a half times a half times a half, that's the same thing as 4 times 1/8. Right? When you multiply fractions together, the product equals the product of the numerators divided by the product of the denominators. Just multiplying these halves together, a half times a half times a half equals 1/8. And we can write 4 times 1/8 as 4 over 8. This is exactly what we would have computed by our older method if we had written out row 3 of Pascal's triangle and noted that these were the outcomes that contributed towards the event. In our old way of thinking, we would be counting up that there are 4 outcomes in the event, divided by 8 different possible outcomes overall in the experiment. So this new method agrees with the old method, but it's much more versatile because the tree diagram method also lets us handle unequally likely outcomes. There's an important idea we've been using implicitly throughout this discussion of shooting at a target, but also of flipping coins, looking at families and observing the birth order of boys and girls, etc. In most of the multi-stage experiments we have been considering, the stages are independent of one another. That expression may mean something to you already, but we're going to use this word independent in a more technical sense. So informally, this means that later stages have no memory of earlier ones, and are not influenced by the earlier ones. When you flip a coin several times, the second coin flip isn't influenced by what happened in the first coin flip. When you have children, whether the second one is a boy or a girl is not influenced by whether the first one was a boy or a girl. For shooting at a target, to say that the shots are independent of one another is a bit more of an assumption, but it's an assumption that we're going to make for the sake of simplicity. In reality, maybe as you take more shots at the target, your aim gets better. Or maybe as you take more shots at the target, you get tired and your aim becomes worse. For our purposes, for the next portion of this course, we're going to be working primarily with independent events. We're going to define this notion of independence more precisely later on. For now, this informal idea, as described here, will be enough. Let's take our new thinking to the next level. Suppose that at the shooting range you hit the target with probability 0.7, and that the result of each shot you take is independent of all other shots. We were really making this independence assumption in the previous example, but now we're just stating it explicitly. You take a total now of 6 shots. What is the probability of exactly 2 hits and 4 misses in that particular order? Now we could draw the tree here, but because we're taking 6 shots, that is rather a complicated tree to draw. At the end of the day, there are 2 to the 6th, which is 64 different outcomes, and that's going to be a lot of drawing. So let's try and answer this question, imagining what the tree would look like, but not drawing it out explicitly. The word in question is hit, hit, miss, miss, miss. And we know that the probability of each hit is 0.7, and of each miss is 0.3, so our probability here of 2 hits and 4 misses in that particular order equals 0.7 squared times 0.3 to the 4th. The important point is, this is one specific outcome, not several outcomes joined together into an event. This is an event with just one outcome. If we had drawn the tree, there would be a path that looked like hit, hit, miss, 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 miss. And that one path would correspond to this outcome. Now what is the probability of 2 misses, followed by 2 hits, followed by 2 misses, in that order? By our same principle of multiplying together the probabilities from each of the stages of the experiment, leading to forming this particular outcome, we've got 2 copies of 0.3, then 2 copies of 0.7, and then another 2 copies of 0.3. But when you gather the 0.7s together, there are 2 of them, and when you gather the 0.3s together, there are 4 of them, so this product equals 0.7 squared times 0.3 to the 4th. And lo and behold, this probability, the probability of this one outcome, is equal to the probability of that outcome. Overall, in this experiment, different outcomes can have different probabilities, but if you have the same number of hits and the same number of misses, after you've done some rearranging, those outcomes have the same probability as one another. Now the crucial follow-up. What is the probability of exactly 2 hits and 4 misses in any order? Now I have to think, what is the number of outcomes in this event? That is, 2 hits and 4 M's in any order. However many outcomes there are, that is how many separate copies of 0.7 squared times 0.3 to the 4th I'm going to be adding up. There are some number of outcomes that fit this description, and each one makes its own contribution of 0.7 squared times 0.3 to the 4th to the total probability of this event. Well, it's a really good thing that we're experts in Pascal's triangle, and in counting the number of words that fit this kind of description. This is exactly 6 choose 2. So 6 choose 2 is the number of outcomes, the number of 6-letter words with 2 of one letter and 4 of the other letter. this many copies of 0.7 squared times 0.3 to the fourth. That is the overall probability, the total probability of this event. It turns out that this is approximately equal to 0.0216. In other words, if you are a 70% shooter, it is very unlikely that you will obtain only 2 hits in 6 shots. It is very unlikely that you will miss 4 times in 6 shots if you are a 70% shooter. Now, a very important contrasting follow-up question: what is the probability of exactly 4 hits and 2 misses in any order? That is quite different. 4 hits and 2 misses from 2 hits and 4 misses. Here again we have a certain number of outcomes. 6 choose 4 different words, and it's true that 6 choose 4 is the same as 6 choose 2, but each outcome in this event is contributing a certain amount, and they all contribute the same amount, namely 0.7 to the fourth times 0.3 squared. The contrast is now crucial. 0.7 is now raised to the 4th power, not to the 2nd power, because there are 4 hits, not 2 hits. Similarly, 0.3 is now raised to the 2nd power, because there are 2 misses, not 4 misses. A typical word here looks like hit, 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 miss, miss, hence the 4 copies of 0.7 and the 2 copies of 0.3, but there are many other words with 4 H's and 2 M's, adds up all of their contributions to the total probability of this event. That total probability turns out to be approximately 0.3241. The probability of 4 hits and 2 misses is much greater than the probability of 2 hits and 4 misses. That makes sense because we're talking about a shooter who is a pretty good shooter. Certainly a better than 50-50 shooter. Before going on to the next video, find the probability of the event that you obtain 2, 3, or 4 hits in any order. For the same experiment of taking 6 independent shots at a target, with a 0.7 probability of a hit on each shot.